Yeah, we'll wait for others to figure it out, I guess.
Yeah, I'm not sure who else will be joining if Wendy is not.
I guess Vikas for sure.
Yeah, so I'm the one who is hosting right now today. Wendy's
I see the word. Yeah, Team TWIML is you. Got it.
So that's the reason you people had some difficulty logging in. I don't know exactly how to do it.
I don't blame you. I don't either. Just technology. Okay, that's probably, yeah. Everybody, well, sometimes, what's his name?
Sujit drops in.
The good doctor. He seems so learned in his ways. Sujit, yeah.
So how are you guys, like how are people able to manage? Like I'm right now playing a catch up. I'm at, I think chapter 11. And last 2 weeks I couldn't do a lot of stuff. So I guess.
Yeah, well, I think we're all playing catch up, it seems. I kind of beat my head against the wall a little bit, like, so I do theory for a while, and then I start to really thinking I'm going to dive into the code, and man, it just slows me down because I'm just not that good, or I don't know exactly a lot about tensors. But I did struggle through, and I finally kind of got into one question that I kind of worked through, figured out, and actually learned a bunch just doing the simple GCN. But then moving into the GraphSage aspect of that one question, there's just like, I have to go back to college and learn like all these things, it seems. So I stopped in midweek and went back and just looked at the videos for 15, just to act like I was trying to stay with the schedule. But that's, how are other people doing it? Kind of managing all the pieces.
Well, I tried to convert the homework to run inside a Colab notebook. Yep. And I don't know, I was trying to convert the options parser argument into like a named tuple, so it kind of seemed like it was running inside the CLI, and I think that's about as far as I got, to be honest. I'm up to the point where it says tuple has
I did that actually earlier in the week. I went ahead and pulled in, there's an argparse, the argparse module. Yeah. You can actually just pull in, and as long as you set the required like options to -F, the requirements flag to -F or something, then you can just use it exactly in line. I should have shared that, but so yeah, you're just trying to get your footing with just the mechanics of some of these programming exercises, right?
Yeah, I mean, I only have like half an hour before the meeting this morning. I was just going to go through that, but it didn't work off the bat for me, so I'm not quite sure what's going on. I'm still digging into that.
Yeah, I've realized that's just like the beginning. You're just kind of peeling the onion back. Then when you finally get into the problem, like here, solve it with GCN, and then solve it with GraphSage, and then solve it with GAT. Well, it's going to take me 4 weeks to understand just what is GraphSage. What does that mean, the aggregators versus the, so I'm learning a bunch. I'm learning so much, but I definitely cannot like act like I'm programming all these things that we're learning.
Yeah. What is GraphSage then? Is there a lot of overlap between these tools, or do you think that they solve different purposes?
I think there are different ways of like making sense of the features.
Okay.
GAT is the attention, where it actually puts weights on the inbound information from neighbors. It weights them so that you can pay attention to ones that matter. You learn which ones matter.
Got it.
That's effectively what, and that's all explained in the videos. And then you start to go to the programming part, and it's like, here, this takes approximately 4 lines. Oh, okay, that helps.
But GraphSage, and what was the other method?
GCN, the very first one.
So GCN is just a generic, what, graph convolutional network, and GraphSage is an actual package for handling that, or?
No, no, it's actually like, I think it's a different approach. I think it's like in a paper. Somebody said, hey, I'm going to try this approach, and I'm going to call it GraphSage.
Okay.
So there is no library called GraphSage, but there's one guy's implementation that everybody uses as their reference.
Right.
And it's not as easy as like I was on that guy's William Leaf did the
so GraphSage is an algorithm kind of like PageRank or something. It's like a way of
more or less
doing it, and they give you a formula, but you have to implement the formula.
Kind of, yeah. I think PageRank is probably even more. It's more of an approach.
Okay.
Versus this is GraphSage is just one technique for basically doing the same thing, which is taking the features out of a graph.
Yeah.
Node features, edge list, and just coming up with a different way to evaluate and learn about that. And it does it through. So it has a concept of aggregations at each step. It somehow aggregates through summing or averaging information from nodes, but that's as far as I got. I was not able to implement it, and I spent more of my time discovering how other people have learned these things on the internet, and they create these forums. A couple of them that I posted were very interesting. People would like take the screenshot from the paper and say, oh, here's how he did that, blah, 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 which is great. But I cannot say I'm progressing through the homeworks to a degree that I think is probably like expected in a class.
Right.
But,
could you share your notebook where you kind of got the parser to run in the argument, the CLI argparse to run inside Colab as is? I think you were saying like -F or something?
Yeah, let me find that.
Because I've got the arguments working, but then it's still saying it can't find batch size. So I'm wondering what the parse optimizer, if that's doing. Doesn't look like parse optimizer actually adds any extra arguments.
Right. That's a -F. Okay, so sharing again. Here I am trying to learn. Oh, learn how to use Zoom. Share. Green button. Share not that desktop, but share that desktop. Then click the word share. Okay, so you should see this one. Right. Okay. Did I see that?
Yeah.
Okay, so I took basically, I started out with the stuff from the first one, which was how to install PyTorch.
Yep.
Okay, good. Then I went ahead and just said, okay, I'm going to play the game. I want to do what the exercise says, count the things, blah, blah, blah. I did this on purpose to make it like a real homework exercise.
Right.
Just getting familiar with how to load the data set. And effectively, we've done this over and over. Okay, great. Now we get into the methods, the GNN stack, which is GCN, I guess. Is GNN stack just another? Yeah. So it allows you, GNN stack allows you to specify which one of the three mechanisms you want to use. And so it does it after you specify it, it builds the module list.
Right.
From this. That's neat. I thought that was pretty cool. So did that. All right. So you wanted to know about this part. I went ahead and kind of broke out the train as a separate function, the test as a separate function. And then I went to the trouble to kind of blow out the beginning as well. So here's the run part.
Yeah, so that's the bit I didn't have. Is like you pass, you kind of simulate sys.argv. So
right.
Yeah, and then
you run the arguments through argparse.
Right.
Or no, it comes from, you instantiate argparse.
Just, yeah. And then you set properties on it and then use that.
Yep, here's, it sets it to this. Where is, oh, there's a bunch of defaults. Where's that? Dave. Where's the, oh, I don't know how to use. Here. These are the defaults which I used.
Yeah.
And then I just for fun print out the at the very beginning. I go ahead and print out the arguments just to know what the heck it's doing.
Yep.
And in this case, it was the default of GCN. And by golly, I got this to work because I finally just made myself understand how just this part works. It took weeks for me to really get a handle on something very simple. Well, let's see. Is that no? I guess that's everything gets confusing after a while.
Did you share the URL of the notebook in the chat or something? I keep trying to.
What?
Could you share the URL of this notebook or share the actual notebook?
Is it just a matter of doing this, or do you have to literally
I'm not sure. Maybe you need to hit the sharing thing.
Yeah, do share. Otherwise, you'll get your same
right.
copy, I think. Yeah.
Add people, get link, copy link. All right. Yeah, I made myself spend a little time on this one just to, go along with doing things in a kind of academic way, but it's very slow. So I was like, hey, I feel pretty good. This was early in the week. I'm like, I'm doing okay. I think I can probably go to the next thing, which is GraphSage. So literally, it's like, oh man, that was the previous week. Sorry.
It's like I need access.
Oh, I don't know. Did I not? I did a share and it said if anybody with that link will get it. Get link restricted. Only people add. Oh, I got to add. So I want to change this. Sorry, I'll do it again.
Yeah, but that should have worked.
Now it does. Now it will.
Okay, cool. Share.
Okay, so that's fine. GCN Stack is great. GCN, I think by default, it built it like we had done before, which now I understand because we spent really so much time on this one, which is great. Thanks for everyone's patience, I think, working through that. Then it's like, okay, let's just move into this new fancy stuff. Bam. I'm like, what the heck is this? I don't know. So I start Googling on this, literally this function, and it turns up, I get these sites in, I assume Chinese that actually go through and explain all this crap. So I'm just learning through this mechanism, not able to dip back in and understand what ag_lin does quite yet. I'm still poking around, finding little pieces of it, but I cannot really land on. I forget where I left off. Yeah, I'm Googling GraphSage PyTorch source code, and you keep getting back to William Leaf's GitHub. GraphSage PyTorch source, yeah. Normally you'll get one guy's GitHub, this person's, and it still doesn't help much, to be honest with you. Something is just not clicking.
I think the Aggregate is the linearized input from the neighbors, right? So
I don't know.
Yeah.
That means I have to actually think about it and know this. Okay, that's the part. So I do appreciate kind of diverging right into.
Yeah, I'm basing it off the Colab 3. That's what I started on with, and I haven't finished it either. But that that talks about the X center and the X neighbors, and the X neighbors is kind of similar to what you have in Aglin, right? It looks similar to that.
Okay, X neighbors. So basically, you're going to go around all your neighbors and aggregate something about them. Their embeddings or something. Oh, that's right. Yeah. Okay, so I'm kind of poking around, but I'm not able to really just like land on code yet, land on doing this. So Colab 3, that is, haven't looked at that. Wendy said that's actually a lot like the homework. So maybe I should. Where is Colab 3?
Yeah, I generally find the collabs to be slightly easier than the homework. So
Yeah.
I was trying the collab 3 first just to make sure that I got it, but I wasn't able to finish that either.
Okay, but is it saying, does it have the same structure? I think
Similar.
they're all done. I think aren't the homeworks done by the same guy like a year, like two
Could
years
be.
ago?
Yeah, could be.
Because they sure look a lot alike.
Yeah, this one basically, in the collab, they basically teach you how to, or they ask you how to define graph sage layers and graph attention network layers.
Yeah, that's
So,
what's asked
yeah.
for in the homeworks, but it doesn't have.
Here,
it
so yeah.
tells us how to do it.
This is a little confusing though, but still, I mean, it's better than nothing.
Right, right. No, this is the normalization across the summation. Okay, and that stuff I learned in these really in these discussion forums. So there is benefit to just bouncing around as long as you keep your focus on kind of the topic. There is a lot of benefit to poking around, but there's certainly a lot of benefit to landing on the right. He actually does it here. Okay. Got it. Okay. Well, this is what I should have spent time on, but didn't. And nice. Okay. So that's kind of where I want to leave the discussion.
All right. So here the lin L and the lin R is basically the left-hand side and the right-hand side. If you go up on the equation, that tells you where, so here. So H, this one, right? The left-hand side of the RHS and the right-hand side of the RHS.
This here?
Yeah, that's the LHS, the left-hand side of the RHS. And, this is basically lin L, right? And this is the plus lin R, right? Whatever follows the plus is lin R.
Okay. Okay, some aggregation.
Yes.
That's summation or possibly mean or sum.
Yeah, exactly.
We're trying to learn these weights.
Yeah.
Okay, lin R, lin L, lin R. And this is for node V. And neighbors, L minus 1 is a neighbor? Or
it's a stage, right? So each layer is basically a stage, right? It goes and looks at its neighbors, and then the next layer looks at its neighbors, and so on, right?
So this is the neighbor aspect.
Yes.
Okay. Okay, well, that makes sense. And this is the aggregating across neighbors. Is this the central thing?
This is the central. Yeah. What weight will you give itself, right?
Oh, okay.
There is also
U and V. Yeah.
So there is also at least in the GCN doesn't explicitly break this up into itself and neighbors. So there you have to add self loops, right?
Oh,
so treat yourself as your neighbor.
That's what a self loop is. I didn't know what a self loop was.
Well, it's a edge going from a node to itself.
So you get some benefit of your own
exactly
embeddings.
Right.
But that's weird. What are you trying to do when you're on a node?
Well, you want to capture at each node, you want to capture the effect of its neighbors and itself, right? So in case of Graph Sage, this is split up in two pieces, right? But with the GCN, it's not. It's basically, just combine everything, give me one weight, and that's how it works, right? So for that, you have to, in order to consider yourself, you have to treat yourself as your neighbor, basically. So you add a self loop.
But even separately, why doesn't it just get aggregated in with the rest of it?
Yeah, so that's the thing, right? I mean, it doesn't, because it's not its own neighbor. But here I don't think you need to, unless they actually talk about it. I'm actually a little bit confused here. So they talk about residual connections, I think, somewhere. So which means like itself. And I'm wondering if I should add self loops here to add itself with its neighbor and consider itself, or if I should leave them separate. But I can, make that decision once I see the training results of the training. So, I'm not too worried about that, basically.
Okay, that sure helps things a lot. I just like seeing that it's got some detail here that then kind of are used when you're actually trying to write the code, like right here. I see. Well, so you actually have to write the code right here, or do the code here. So, okay.
Yeah, basically they're telling you what you have to fill up, like the self lin L and the lin R.
Linear
So,
transformation.
yeah.
Okay, and there's linear functions, just straight linear
Yeah.
NN from
Yeah, exactly.
graph.
So if you see the equation, it's like WHL, right? And that should translate immediately into a linear, this is basically a linear layer, right?
Mhm.
You have a single weight and, you're multiplying it by a weight. So you're rotating the the vector. So yeah, so this is basically, this represents one linear layer. The second term represents another linear layer.
So you define a function and then pass that function in order to answer that question below? It's like a lambda, like a one-line function or something, or you're just adding a value?
You're declaring a linear layer, which is to be trained, right? This is an init. So here you're just saying that, I want a linear layer that will represent that piece of the right-hand side. And the W in that term, in both, right? There is a W. So W represents the trainable weights, right? The learnable weights of the network that you will learn over through backpropagation.
This is just a layer.
Yeah, this is just a layer, exactly.
So should I
This
have a
will be
module list? Should I make a?
No, not here. So if you go up, you will see the layer being called, right? So in the block previous to this, they actually declared the entire network. Go up, like previous cell. So I think this one, yeah, yes. So this is, oh, they call it GCN Stack. I didn't realize that. So it's exactly the same thing.
Right. So that's okay. So we care a lot about the building of the model, which is done.
So essentially, this is a way to switch out different layers. I think the objective would be to train them with different layers and see the results, how effective they are. So if you see here, right, the build the build conf, the conf model equals self build call in init, or I think second line init. So that calls this guy, and depending on what model type you want, right, what model type you have specified, it will actually either include a graph sage or a GAT.
But it defaults to GCN.
It defaults to GAT in this case.
Oh,
right,
oh, right.
or not maybe.
You're
No,
right.
There's no default, right?
There is no default here.
Oh,
yeah. Well, unlike the homework in that case. So the homework and the collab seem to be very related here.
Okay, so on the init, the model gets built here, and it's used in the list after it goes through. This is the first layer, input, then hidden, then 1, 2 number layers minus 1 of hidden layers, and then one final layer at the end. Yes, the message passing is a layer itself, right?
These are actually just plain old linear layers. I don't think so. How they are connected is in the forward, right? These are just standalone layers that you have declared. So now this is how they're connected, and really the message passing thing is not even declared here. They are inside the graph sage and the GAT, right? That's where you do the forward and the propagate, which calls propagate.
Yep. Okay.
Right.
So it's in this model that does the propagate. Isn't the message passing though? It's showing up right here at the right here. Right at the it goes through all the layers, and then last thing it does is the message
self post MP
layer.
Well, I don't know what post MP is. I don't, I haven't learned that yet, I guess.
It wasn't
after message passing, post.
Right here.
Yeah, post message passing, I would assume, but
it's a layer right here.
Oh, I see. Okay, so it's just a sequential layer.
Okay.
So this is not doing the message passing though, right? This is after message passing in the the GAT or the sage graph sage thing
in this place.
Right. And that you can see if you go into the graph sage, then the next cell, that's where you will see the forward calling, propagate calling, message, whatever, this whole thing here. Well, he sends you to a link here. This one. right? This one talks about how everything fits together.
Yes, I've done this. I've followed that before. That is very helpful, that one. It's probably one of these recent ones. No. Yeah, I think I got like breadcrumbs of my previous work. So that, okay, that kind of lays out the basics of how this works.
And see, this is what I was talking about. If you look under def forward, edge index and add self loops, right? In step 1. Yeah, this is for a GCN. I don't think it applies for GraphSage, but you know, I don't know yet, so I might add that in later on, depending on what I get.
Does that add self loops basically for every node? It's not selective. It's just saying.
Yes, you just add self loops to every node. That way, every node behaves as its own neighbor.
Got it.
On each.
And why would you kind of bias the network to do that?
Because GCN does not explicitly take into account yourself. You know, so it basically says, give me the average of my neighbors, right? Neighbor features. And so if you want yourself to be included in your neighbors, you do a self loop. That way, you know, you get added to your list of neighbors.
Right.
And you get, you know,
Oh, that's true.
Is there any weight on those edges? I guess this particular algorithm doesn't deal with weighted edges.
Just updates.
It's just a connection to the node.
Well, there's no weight. There's no place for the weight.
It's it'll be 1, right? I mean, you're just considering yourself.
Got it.
Okay.
Yeah, this confused me for a while. I had to think about it. I mean, why would I do this? You know, it's kind of dumb, but you know, then I realized,
yeah, I'm still wondering about like.
Your answer would be, if you go to the GCN's equation, you will not find itself being considered, right? So the equation for HL plus 1 only consists of or is only an aggregation of its neighbors, right? Of node I, HL plus 1 node I consists of an aggregation of HL of node J, where J are the neighbors of I. Right. So then you don't consider yourself unless you act at the self loop.
Yeah. Okay. Okay. So that is. Stuff is still a little bit blurry, but kind of working through, like going it step by step has helped. So this here is defining the layers.
Yeah, it's an NN linear, which basically takes, you know, your hidden input size and hidden size, I guess.
Right.
In channels, hidden channels, I guess, for the node.
Okay, something like that. I'm not doing the right code, but they're just linear layers of the neural network class that's taking the inputs. I
think in channels and out channels would be what you want.
Something like that.
So self.in channels.
That's true.
Yes. Always better to do that. That way you can.
Oh yeah.
Well, I guess they're parameters anyway, but
yeah. Well, here it doesn't matter because you're still in init, but it's always good practice too. Yeah,
and actually, just in case, just to be more proper, that might not even be proper. That might not even be right, but
it's actually not right. But you know, it's fine. Right. I mean, as long as the document itself, you know, it's for you.
Right. It's not. I'm not going to run this. So you define 2 linear layers. That's the second one. Where's the aggregator come in?
It's the same size, I think, because it's aggregated down to, you know, it's like 1 node's worth of stuff, basically just aggregated across, you know, multiple nodes worth of stuff divided by the, you know, the aggregate, right? So it's like it's summed. So basically it comes back to the same dimension.
We have to. how do we aggregate? How do we actually implement this?
Oh, so this is just taking the mean here, right? You're taking the hidden states for the previous state for all its neighbors, and you're summing them up, dividing by the number of neighbors. So it's a mean. Okay.
Again, I'm. This is kind of where I kind of see the code, but I don't quite know what it's doing. That's okay. I'll like this has to be plus some ag stuff, right?
No, this does, well, you will aggregate it inside your aggregate function, but that'll come later, I think. But you can,
Really?
you can put a comment or something. Yeah.
Is there an aggregation function?
I believe so. Message and then aggregate. There you go. Yeah.
So I got to, I have to do some plus some.
No, you don't actually. So your output will be the output of linear 1 and linear 2. Those correspond to the left and the right hand side. The first term and the second term on the right hand side of the equation. At least that's what I think. I haven't I haven't tested it, but I got this piece done. Okay. But that's about it. And then I stopped because I didn't have time.
Okay, I think it may be an aggregate.
Yeah.
Something. Inputs. I got to figure this part out. That's probably no big deal. Aggregate of. Oh, we got to write the damn thing. Uh-oh, shoot. It's always something. All right. Well, okay. That's kind of the.
Yeah. The thing to know here is that forward will call aggregate, and aggregate will call message, and then something else. Oh wait. So no, that's not right. I have it written down somewhere. Hang on.
Forward.
It's probably better to look at my code.
Let's see, forward. Well, it would call forward has to call everything.
Yeah, forward will call aggregate and aggregate will call something else. So give me a second. I have it written down. It's basically there in the write-up, but I thought it was very confusing, so I wrote my own little version.
Yeah, I see. It is. It's in text, but
yes,
you're right. All logic in each iteration happens in the forward. But,
okay, so forward calls propagate, and propagate calls message, aggregate, and update. So here you can drop one or the other. So I think they're asking you to drop the update and push it into the aggregate or something. The functionality update, they're asking you to push into update, I think, something like that.
All right. This calls propagate. Is that right?
Propagate.
Oh, wait. Sorry. Forward calls propagate.
Propagate calls message, aggregate, and update.
Okay, message, aggregate, and update. Forward calls propagate. And then what calls message and aggregate?
Propagate will call these three: the message, aggregate, and update.
Where is propagate? Is that? I don't see propagate.
Propagate is not defined here. You just have to know that,
it's a part of the super.
Yes.
Okay. But it automatically. Oh yeah. So propagate automatically calls these two, message and aggregate. But as long as we get propagate, we get these as part of the call.
Yes.
Okay. And.
Oh no! Wait. Yeah. So what I have done here, in the forward function, the first thing I called was self propagate to get my X neighbor, and this is part of the instructions. It's kind of vague, but so I had to call self propagate to get the X neighbor, and then self central is basically just a linear layer on top of the X. And then, then you have to normalize. So yeah.
So there's a self-propagate at the beginning of the forward function?
Yes.
Okay. Huh. Oops, good Lord. And that, okay, maybe. That gets you, let's see, that gets the neighbors.
That gets your neighbors.
Message.
So, yeah.
Oh.
So ideally, you should write this stuff inside the to-do block. I mean, just it's up to you. But and that corresponds to instruction number 1, I think. First call propagate function to conduct the message passing.
Got it. Okay. Well, that will be helpful. And that's basically darn it. I'll make a little bit of a note here. And then that is you're doing this little step right here. Generally, the forward function is the actual all logic. We'll call propagate to propagate the information from neighbor nodes to central nodes. So this is where, can I edit that?
Yeah, 1.2, I'm not actually really sure what he means. But, I'm sure I'll find out when I try to run this thing.
Okay, well, that helps me at least a little bit. Those little stars right there is where you call the self.propagate. And then you do this is now no longer needed. Is that all it does is?
Well, then you have to add the left-hand piece, right?
Right.
So you basically pass it through self-lineal,
okay.
The input signal. And then I've used, so if normalize, then, that is step number 3, right? If normalize, I basically ran it through normalize, functional normalize, just as they told me to. And now I'm just doing a torch cat of X central and X neighbor. And I think, I may be wrong here. I'm not sure. Maybe I should do X central plus X neighbor. And maybe that's, that's what I should do. Yeah.
So there's a possible, you have to concatenate. Yeah, you're allowed to concatenate the information. That's the whole parallelization of it, right?
Exactly, right.
Normalize and then possibly.
So I have to experiment there. So since I haven't, done this, so I don't know yet.
This is wrong. Okay, that kind of helps me kind of give a little bit of a start to the flow, which is really, that's kind of the important, that's the learning part, is to take kind of what makes sense in slides and paragraphs and turn it into code.
Right.
I see, that's a normalization right there. Which is average? No, what's L2 is, what's normalization?
I think it's L2 normalization. So, and that is default, I think. So if you look at
just call normalize and then dot something.
Yeah, that's pretty much torsion and functional normalize.
Okay. Okay. Well,
let me double check that.
Pretty useful.
Yeah. So if you go to the the page for it, the documentation for normalize.
Yeah, I probably already have it up here somewhere. But
so it says P equals 2. I think this is the norm. right? So default is 2, so you don't need it. So you're just doing L2,
Okay.
right?
Okay. So it looks something like, so that's, you're continuing to kind of work with the out function.
Mhm.
I don't know if it's exactly, well, it's a function in the neural net. What library is it from?
Which one? Oh,
Is-
torch and then functional.
Torch,
Normalize.
okay, torch, and then
Functional normalize.
functional. Is it F or does it actually?
No, a small f.
Sometimes that comes in as capital F if it's
Right,
been.
right. Yeah.
Yeah.
And small normalize, small n.
I was hoping to get the completion.
Yeah, it
Oh,
doesn't
well.
seem to give you that.
I think it's sometimes whatever memory is available on the machine to pull in all that. Yeah. So it might be as simple as this, but it usually isn't.
Yeah. So I think it might be just, if you maybe now that I'm thinking about it, it could be like out equals x neighbor plus x central, and then we just send normalize out. That seems more reasonable, but we'll see.
Where is that? So we don't have it called an x central or neighbor.
I don't know where I got the x central thing.
Okay, let's think about this.
Oh, there it is. So if you go up in if you go up in this area, right? So you'll see here x central and x neighbor represent.
The first
Here,
place
you're there.
Yeah.
Right. So, okay.
X equal x central. Okay.
There you go. Yeah.
That's yourself, right? Okay.
Yes.
In order to complete the work, we have to understand how they interact with each other. Propagate, we can pass any parameters. For example, we pass x as a parameter. Oh, should we do that? And what is, I don't know where we have this defined. Oh, sorry. Central nodes and neighbor nodes. That's like, and yeah, okay. So, like, is it, how do we index to get central versus neighbor? Well, we've already added the self loop.
Yeah, so this part is a little bit confusing here, but the way I came up with it is that, x central is itself passed through a nonlinearity, like a linear layer, and x neighbor is the output of propagate, right? Now propagate we know calls message and then aggregate. So in the message, we basically construct this whole thing, right? So this is the message that will come from each of my neighbors, the XJs, right? So essentially what I'm doing is I'm creating an out here, which is I pass in through this second linear layer, right? My neighbor linear layer, the lin R, right? So either that or actually no, I think I'm wrong. I think is basically out is the same as XJ, right? You're not doing anything. And then in the aggregate, you want to basically add them up, right? And then send it back out of aggregate. And that's where you catch it, right? When
the neighbors.
In the neighbor, you do self lin R, and then you take the output of propagate. Yeah.
Okay. I'm not making enough sense of it to actually type things. So, but that's okay, because I think just that whole attention to how the words and the formulas play into where the things are happening.
Yeah.
It does seem to, there's enough breadcrumbs in here. You can tell everything is here to do the work.
Yes. Yes.
So I like to know
everything is here, but it's kind of
well,
somewhat vague, I think. But
that's the way all these are. That's the way this is. This is pretty vague. It makes sense when he says the words, and the pictures are nice, and I understand what he means. Then he says, okay, this becomes like a 3-week function that I have to implement. which is fine. I'm not complaining. I'm just saying that's the nature of complex versus complicated
Right.
versus elegance. I mean, I'm just amazed. Like I don't know if you've looked at chapter 15. How he's going to generate this graph.
Yes. Yes. Yeah.
One node at a time, with using nothing but a probability expectation of probability is just brilliant. Like, oh, that's so simple.
Yeah. Yeah, at least from the NLP perspective, I don't know how good it will be, but we'll see. Yeah. So
I see. So you've got some experience with trying to do the same thing with
yes.
sentences and words following words, and
Mhm.
you know how awry that can go
Yes, exactly.
because of the complex relationship between the sensibility between words that are
Right.
connected to each other. But this is maybe slightly different with the social networks, or
Yeah, could be. Yeah, definitely. Yeah.
but I love the idea of the coin flip, the teacher part. So if anybody hasn't got into 15, you coerce the weights simply by telling it what the actual edge is after you guess it.
Yeah.
You know, you guess it because you are originally coming up with what you think is a probability, starting out with, I think, a random, just like everything, kind of starting out random, and you coerce, you learn with a teacher imposed influence during training. It's great stuff. I'm pretty,
it is, yeah.
pretty impressed. Yeah.
Okay, I'm going to have to drop because I got to take my mom to the doctor.
Okay.
So,
Well,
that's the last. Yeah.
I think we're getting close to wrapping up.
Yeah, I think so. Yeah. Well,
Thanks,
anyway,
Sujit.
yeah, sure.
Appreciate
You're welcome.
it.
Right.
Yep.
Absolutely. Right.
All right.
Bye.
Bye-bye. All right, other folks. Just want to kind of do a check. So I guess the concept is here, this is this week. This 15 is all about the generative, trying to predict, trying to generate new networks that are as much as like a previous network as possible. Good stuff, but it's like a whole new topic than what we're just talking about. So
it's not so much predicting, it's generating like similar networks.
yes.
It's not generating kind of paths off the current network. It's taking the current network like a seed and trying to generate another similar network.
Right.
Okay. Interesting.
It is, and it's I can't think of a use case except the classic molecule. You're trying to make a new molecule that's as much like a molecule that you know about as possible. Right. And
why wouldn't you just take the original one and like change a bunch of stuff?
Well, I mean, I think the idea is that you can start from scratch, or maybe start with something that you do already have, like a base chemical. I don't know. That's way out of my understanding.
Right.
Where graph generation? Oh, I'm already on it. I don't know why I was here. I was looking, maybe, didn't we discuss this a previous time? Maybe not, I don't know. But yeah, so if you read that, and I'll just touch on some things that I thought were pretty interesting. The idea that you have a model that is represents like an ideal. I can't explain it. That's beyond my ability. Back to the chain rule. So if you have this probabilistic model, you can just use the chain rule and add up all the probabilities to represent the probability from this one node. It's all the, I guess all the probabilities of predicting one node from all the previous nodes, all the probabilities of all the previous nodes. That doesn't explain it at all. It's like this. You start with 1, and then you add a node, and then you add the edge back to that node. Then you add another node. This is pretty straightforward, but the magic happens when, should you add that link or not between 2 and 1?
Mm-hmm.
You do it probabilistically, and then during training, you are told whether it was there or not. And then you can, through back propagation, you know, do the normal, like whatever the normal aspect is for weights, where you're actually learning the weights. You're actually, you know, learning which ones mattered by the imposition of what the teacher told you was actually there. It's laid out.
So, just a second. In the previous, yeah. So creation of this. Yeah.
Oh,
So when you're creating fourth, I have not gone through this chapter yet. So, but when you're creating this fourth node, so it contains 2 connections, 1 to 2, 1 to 3. So are those 2 steps of like creation while creating this?
right. Well, you first have to create nodes, then you have to create edges.
Yeah. So we have 1 and 3, and then when we are this fourth, you have 2 connections, 1 to 2, 1 to 3. So are those 2 different steps? I mean, I haven't gone through the chapter, just saying this. So are they going through 2 steps, or it's a single step? So for example, even the 5th one, the last one.
Right. No, it's he does break it out to, there are node. You first add a node, and then you go around and add the edges. But it is, I don't know about steps. I'm sure you have to cycle through. You have to basically go to every neighbor and say, should I have an edge here? Yes or no? And it's the weights represent whether you should or not. And if you were wrong, then the back propagation process will change that weight. You're learning that weight, which would, of course, it does it through what would, as he says, you learn it. Here it's an RNN that basically, here you're cranking through. You're generating the adjacency matrix on the fly, kind of through this RNN. Each step of the RNN creates more and more of the adjacency matrix as you're creating more nodes. And the training is using just regular cross entropy loss to get dinged when you make the wrong decision. So that is at training time. You start out with a probability, but you do have a known, this is the teacher telling you what they call teacher forcing. Here it is, teacher forcing. And of course, during training, you can just do the evaluation, which you want to maximize this equation. So you want to force, in this case, you want to force this to 1 and this to 0 to get the log of 1. Log of 0 is 1. So this will leave y1. You get the idea, right? You're gonna learn how far off you are over time with back, and it back propagates all the way back through the entire sequence. So this is, yeah, I mean, it's all spelled out here. It's pretty great. I mean, that's why every lecture is. It's like, oh, that makes total sense. But I cannot imagine coding this. This is going to get crazy. As it all has. It's all been very out there. Yep. Okay. Well, we've kind of run up against it, but that was kind of 15, is this very interesting aspect of generating graphs with things that we know how to do. We're just applying these concepts of RNNs and 2 adjacency matrices. that we generate on the fly.
What's the meaning of the coloring on there? So on that observed graph in the top right.
Nodes. Well, this is the adjacency matrix, which represents edges.
Yeah.
Why is it yellow? Good question. I haven't gotten that far. I'm literally right. I'm about right here.
Yeah. I mean, he's showing the edges being added, but I'm not sure if the color is some way of reading those 3 nodes. Like
they obviously do have some connection. So let's kind of start with
those are the start points, I guess, because like 1 and 3.
Okay, we start here with this signal called start of sequence.
Yeah.
Okay, so it says it gets an actual input that says, okay, now you should begin, which is interesting in and of itself. Now, why is it already started with a graph?
Yeah, why has it got 3 nodes already? Unless that was what it was trained on.
No. It's going to get much bigger than this.
This is observed graph, right?
Because there's observed graph and there's generated graph. Doesn't observed graph means what it viewed?
Yeah, that might be true. Maybe this is just this is an example of how this works. Giving that we have a node of, okay, so this is obviously the adjacency matrix for this 1, 2, 3. Is that right? 1 and 2, 0, 1. I'm sorry, 1, 2, 3, 1, 2, 3. 1 connects to 2. That's row.
Yeah,
row 1, column 2. 1 connects to 2, and 1 connects to 3. 2 connects to 1, and not anything else. 3 connects to 1, and not, okay. So this is obviously reality.
Yeah.
And we can just kind of figure this out backwards. We always got to start with 1, I assume. So he asks, will node, maybe you got to start with at least 2. You know you're going to have at least 2 nodes. And as a matter of fact, you could almost assume you're always going to have at least, this is the minimum reality is 1 and 2 with a edge, right? I don't know. I'm just making that up, but.
Yeah, but this seems, if it was trained on the original graph, won't it just generate an identical graph, or will it generate something with a more
let's see. Good question. We're trying to learn the weights of this model. He does at the beginning say, we don't really know what this is. We only have some kind of a representation of it. We literally don't know, which that's what the model is. Okay, so back to kind of the beginning is this big blue P model.
Yeah.
Just represents some probabilistic aspect of.
I mean, is there any randomness when you're generating these things? If it's running the same calculation each time?
I think it's sampling.
Okay.
So our model is I think just a probabilistic model, and we are sampling from it.
So sample with a simple noise distribution means that noise distribution changes every time you sample it, so you get like a different sample basically.
Right. And I think this is
so it's a much more compact way of memorizing the network because you're sampling bits of it as opposed to.
That's exactly right.
Right.
So what's amazing is that you can take a complex graph and actually encode it in a way that it's a much, much smaller representation.
Right.
But you can use this representation to generate a new graph, which is very much like this in structure and content, but not exactly like it.
But don't you still need all those kind of in-between transformer layers? I mean, when you train a model.
No. I think that's the point.
Right.
I think that you can represent. He said normally we've been working on making graphs and how to figure out how to turn it into these little things. Now we're going to start with these little things and we're going to generate the graph.
Yeah.
Through this generative process.
But I mean, the model isn't just the final layer. The model presumably includes all those kind of hidden layers and everything in the middle, like the data for them.
Well, let's say they don't. Let's say all you have is the weights
Okay.
and you want to generate a big ass graph.
Yeah.
Well, here's how you do it.
Right. And those weights are presumably, that's the sample, right? The sample size, maybe.
Well, the weights are used to generate this guess.
Yeah.
When you're guessing before you're told, well, wait a minute now, that's the training. Now you're kind of pushing me on what I think I know, which is okay. That's kind of what the nature of. Okay, at test time, not training, at test time, we've already trained the model, which means we have the little representation.
Mm.
And so you use that representation to guess whether you should have a new node or not after just the first thing.
Mm.
And that's the input to the next. That doesn't feel right either. Okay, well, we don't need to go into crazy places that I'm not familiar with, but it's. I mean, we're able to, I think, at least understand pieces of it enough where the lectures make sense, and they kind of tease you to want to get into it to the degree that we can understand the coding, which I'm sure is going to happen very soon. But yes, I mean, we blew through so many lectures that we really didn't touch on much. But are they mostly just in support of what we've talked about already in the homeworks and things?
I have no idea. I haven't been looking at them, so I don't know.
Yeah. Well, let's see. We just touched on this. Community structure, we really didn't talk much about that either. And that was, I think, kind of interesting, how to be able to determine local communities in graphs. That hasn't been brought out in any of the as far as I know, none of the homeworks have dealt with communities. Are we just going to blow through that? You know, like this doesn't tell me anything about communities, does it? I think this just kind of lets you classify stuff. Or is that part of it? Is that where you would classify a little graph as a community? I don't know. You know, the node prediction or graph prediction. That's where a lot of this stuff, like, where's real life come into here? Where's, like, show me a picture of a real problem you're trying to solve and work me through how we're using these to solve the problem.
Right.
Maybe that's CS225.
That's what you get paid money for, isn't it?
Oh, that's right. You're supposed to actually do that for a living.
Right.
Okay.
I'm actually working on a like a NFT artwork, and I'm using graphs as a kind of way to generate artwork based on like a blockchain hash. So I've got like an actual application for it, and then obviously some kind of work related stuff as well. But
Right. I know you were trying to deal with like software or coding or
I'm mostly dealing with conversation analysis, so conversationless graphs.
Conversation as in back and forth in a Slack channel.
Talking to chatbots and then trying to train the chatbot on like previous conversations to answer the questions in future. That's the idea anyway. But I haven't actually got to applying any of this stuff to that yet.
Right. You're just trying to arm yourself with some knowledge about how to approach that problem.
Exactly.
I know Yuri has a background in some NLP stuff. He could probably be interested in maybe having some input into that at some point.
Is that right, Yuri?
Yeah, so I haven't done a lot of homeworks, but I'm interested in trying to do the knowledge base based homeworks.
Right. Yeah. So are you doing NLP stuff?
Yeah. So actually, we don't. I guess we can call it knowledge base, but we have So we do. We have our own ontology, and we trying to automatically map data description into our data description.
I thought it was,
and
but not
yeah,
conversational.
but using NLP, yeah. So it's a
Okay.
textual description. We might do bots at some point, but right now it's it's like a future goal, right?
Okay. Other text, other bodies of text.
And are you
Yeah, go ahead.
are you extracting knowledge from just free-form text, or is it more of
That's also like that's more immediate goal than actually bots, but yeah, we're planning to do that also.
but right now it's more like an ontology that someone has kind of manually built, like this relates to this, like the graph?
Yeah, so we have our own ontology, and it's in the graph structure, and we're integrating, basically mapping other ontologies, which typically also have graph structure.
Yeah.
So we have our own methods of sort of like combining graphs and NLP embeddings, but I'm trying to see if actually we can switch to using of one of the
Cool. And is the goal to map one to the other, or at least find nodes in one that are similar to nodes in the other?
Oh no! We are doing it like we're doing it manually. Like right now, people are doing it manually, and like analysts like doing it. So if we can do 70-80% of mapping, we save a lot of time.
Well, that could be your training data, right?
Yeah. So what people done before, that's our training data.
Yeah, that's interesting. So the whole concept of using a conversational though to do what? What would Dave and your want to engage the bot?
Yeah, our stuff is mostly for like customer support.
Right.
So we have a lot of conversations between humans and customers, like support agents.
Okay.
We automate more and more of that by training on kind of transcripts of previous conversations.
Yeah. I kind of get the idea of a bot asking questions to try to help characterize the question properly, the problem into a very specified problem area.
Yeah.
Actually solving the problem, suggesting answers, that's a whole nother problem.
Yeah, I mean, it depends on the complexity of problems. I mean, if you're just, for example, doing like a simple troubleshooting bot, then effectively you're learning an expert system by probing previous conversations, or at a very basic layer, a doctor giving a diagnosis, he'll ask like, what's your temperature, what's this, what's that, and then in theory you could create kind of like a tree structure out of that.
Sure. Almost your basic decision tree approach.
Yeah. And a lot of this stuff is very repetitive. I mean, obviously, there's the image of very complicated things that AI tries to solve, but it's the 80-20 rule. Like 80% of the calls coming in are really, basic questions, and so they're perfect for automation.
Right.
And then if you get to the end of that, at the very least, you've kind of probed, like you said, you've gathered requirements, and then you can hand it off to a human to just deal with it based on that summary.
Okay.
That's the idea anyway.
Yeah. No, that sounds very doable. That's what
easy for you to say.
That's what they told you. Yeah. Oh,
that's what I felt when I started this course as well. But anyway.
This is in different places than that. But it's I'm sure it's going to help inform something along the way.
Yeah, I mean, there's different layers. There's actually extracting meaning from the user's conversations and turning that into something that's kind of useful enough to train on, and then recognizing when new users come in, like trying to map their questions to things that you've got in your previous graph, and then there's predicting replies. So there's like a whole pipeline of different stuff.
I'll bet. Gosh, I cannot imagine. It's almost like I mean, most NLP stuff is kind of fascinating anyway, because you're tokenizing and trying to really generalize the tokens and the sequence of tokens just to make, just to give it something to work with.
Yeah. But I mean, the thing is, it's actually theoretically possible, I think, if you're training on a kind of fixed base of knowledge. So if it was like a medical thing or something like that, a lot of the problem for us is that the calls also contain very specific, like, you know, what's your phone number, or like, how much is my bill, or, you know, those kind of things, which, so they're kind of like outside influences. So we can't simply do it by just answering based on previous conversations, because you might give someone else, like, you know, someone else's billing information or something like that, you know. Right. So you kind of interject like the stuff that is in your kind of static knowledge graph with, it's like templating, basically injecting like user specific information.
Oh, that's interesting too. Yeah, because that's very powerful to help the pipeline of problem solving, just to get them into a template.
Yeah, basically.
Then just dip into the database and pull out the balance.
Yeah, exactly. It's the same problem, but just different parameters, basically. Yeah.
Cool.
But then the other thing I was doing with the NFT stuff is just a fun art project. So I'm trying to generate graphs based on a blockchain hash, but more as just something that is interesting to look at. But the actual code that generates that goes on to the blockchain. That's how me and a friend are doing this project. So anyone who buys one of these things has it in perpetuity, but it will generate a different graph every time based on the hash of the final block. So it has to be pretty compact, and I'm doing that in JavaScript. So I've been looking at a few algorithms like Dijkstra's, however you say that, and kind of traveling salesman and those kind of things, just ways of walking through graphs. It was a way of having a very compact way to generate a graph that would be interesting. And then you could effectively just use a hash to seed that generator and have it generate a graph. It's kind of like a fractal pattern generated on some.
Right.
But the problem is you'd need like all of PyTorch to do that from what I'm looking at here. I'm really, because like the whole code of this thing has to fit in like 20K, because it's insanely expensive to produce a contract where you're putting all the code on the blockchain itself. So I was looking for something much more compact. I was also looking at ways that people, like the algorithms for rendering these things, like the force diagrams, where you see those graphs that kind of just resolve themselves, so based on like almost like a physics simulation. But that's more on.
That's cool. That's like, so the visualization would be the graph.
Yeah.
And actually what they're buying is the actual final visualization, but you want it to be embedded into the blockchain so that it has all the benefits of authenticity.
Yeah, authenticity, and also that, like, if, you know, whatever company goes away, like you don't want to just put the image on a server somewhere, like, and putting an image into the graph would be like a 2 megabyte image or something. So we're putting the code that generates the image into the chain, and then it's, I mean, last time I did it, it cost about $2,000 just to do the first contract. But then every time someone prints one, they're basically buying an invocation of that contract. So it's just like calling the function. So setting it up, and that was only for like 18K of code. So, you know, you can't really like a 2 megabyte JPEG.
Right. No. That's ridiculous. But having some very efficient representation.
Yeah, exactly.
That is that's cool. So basically you could start with a big 2 megabyte, full resolution picture, and the concept is come up with a way to represent that in a much smaller version.
But the other thing is that we do have the random seed of like the actual hash. So when someone prints a copy of the contract gets fed in the block, like the last block that corresponds to that, what that person bought. And then we use that block, which is just like a 32 byte string, and then that's used as a seed to generate the image. But you know, so if there was a way of using one of these techniques of generating graphs based on a seed, then that would be pretty useful. That would be pretty interesting.
I see. Wow, that's out there. That's out there, man. Okay. I kind of basically understand parts of what you said about the blockchain and kind of how it generates, but not fully. Although I could see then if that was true, then it sure would be nice if there was a way to represent.
Yeah, exactly. Yeah. So it is like probabilistic, because you want it to generate the same image every time for the same kind of print. But if someone else gets another print, they want to have something that looks similar but different enough. So like the shape of the graph or the colors or all that kind of thing would change based on it.
Oh, that's very cool.
But
yeah, I mean, there's been some work done on representing images in a graph with different techniques for how to represent neighbors, and little regions, little zones where you have one near neighbor, and then you have the next layer out, or maybe you have some average of some power function that represents the colors of the pixels that are furthest away from you. And when you combine all that together, it makes the picture again, yet the representation was much simpler than every pixel.
Right. Yeah, but I'm not sure. I mean, if it needs all of like PyTorch, that kind of, it's a bit like my application. Yeah, I've got something that looks like this at the moment. So you can actually speak into it as well, and it will record those things. But at the moment, it's just taking a random, it's taking the seed from the blockchain. So if I click on like token 2, that feeds it with like a different hash. And every time you hit token 2, it should start with the exact same pattern. And then it's looking for edges that are close to each other. So 2 and 3 is connected, 5 is connected, the E's are connected. And then it's just running the most inefficient sort algorithm on the adjacency map to kind of move the pieces around and try and sort the chain. But anyway,
yeah, that's great.
Now,
very interesting material.
Turn it into something, I hope. Yeah.
Oh gosh, I'll bet you will.
By next week, maybe.
Oh,
but
good luck with that. But
anyway,
that's cool. Very good. Thanks for that demo.
Okay. Good stuff.
Okay. Yep. All right. Well, we'll do our best to kind of plow through maybe Colab 3 pieces of it now that we have a little bit of a head start from Sujit. And
the links into that sheet that we've got as well, because it's always a little bit hard digging around for these things. But yeah, sounds good.
All right.
See you guys.
Take care. Have a good week.
Everybody. Cheerio.
See you, Vikas.
Yeah.
Bye, Yuri.
Okay. Bye.